The last little bit of theory for graphical linear programming is to look at situations where there are multiple optimal solutions to an LP, or to a linear program, if you like. Okay, sometimes shortened to an LP. Okay, so let's have a look at an example. So these constraints for this question were taken directly from one of my examples from the first video. I've just changed the objective function a little bit to meet the needs for this, what I'm trying to illustrate here. Okay, so what I've done is I've just taken these 4 constraints, I've graphed them, I've found the feasible region, and I've found the vertices of those feasible regions. Okay, that's things that we've been doing in linear programming since the start of this little section of modeling with algorithms. So the next thing to do would be to take these 4 points and plug them through my objective function, which is 10x plus 10y in this case, and I'm going to record those values over here. So calculator out. At the point A, we've got x is 28 thirds, and then at the point B, we've got y is 8. Sorry, at the point A, y is 8. So P is 173 and a third. I'll put that there. Okay, now repeat that process, but for these other points. So 10 times 12 plus 10 times 6 is 180. 10 times 40 thirds plus 10 times 20 thirds is 200. And 10 times 12 plus 10 times 8 is 200. All right, so in this situation, we are looking to maximize our objective function. Okay, maximize, I'll call it P. Didn't call it P up here, but I want to maximize P. But in looking at my P values, I can see that both of those values are actually the same. Okay, so this was C and D, so that's this point here and this point here. So what we actually find is, yes, those two values both have a P value of 200, but in fact, more so than that, every point in between those 2 points on that linear line there, every point there would have also a P value of 200. What has happened, if you think back to my video on the objective line method, is the objective line, which in this case is 10x plus 10y, is parallel to that constraint. So when you're moving the objective line up towards the end of the feasible region, it hits both of those points at the same time, and then both of those points will leave that at the same time as well. So we find that all of those points on that line have the same value, and there are essentially infinite solutions to this linear programming problem. Okay? And that's essentially it. That's all there is to the situation. So let's have a look at a similar example. This was taken from my second video in the linear programming series, which was a minimization problem. But again, I've just changed the objective function to meet my needs for this video. So here's my graph, here's my feasible region, and here are my vertices. And I'm just going to run these vertices through the objective function. Okay, now the objective function, I can't quite get it on the page. It's 8x minus 2y, 8x minus 2y. Okay, so we're going to do 8 times 7 minus 2 times 24, that's 8. Here we're going to do 8 times 5 minus 2 times 16, that's also 8. We're going to do 8 times 5 minus 2 times 12.5, that's 15. And then we're going to do 8 times 10 minus 2 times 10, which is 60. So we want to minimize C now, either maximize, so taking the smallest, again, we can see there are 2 solutions there, A and B. So that means that, yes, the C value at those 2 is the minimum it can be, but also any point in between those will also have that same C value of 8. Okay, so the minimum value of C is 8, and there are multiple solutions to it. Occasionally, an exam question will kind of approach this from the opposite way, and it will say, okay, given that these 2 points are optimal, then find the coefficient, and you would need to know that the gradient of the line in between the 2 points, which have the same objective value, is parallel then to the objective line, and you just work that area of maths to get out the one of the coefficients. Okay, so the converse is true. So if 2 points both give the same objective value and that's optimal, then that means the objective line is parallel to that constraint, and you use that knowledge to find a coefficient. Okay, right, that's it for this video. Nice short one to finish up linear programming graphical methods. I hope that's been okay. I hope that's been very informative for you. Again, if you have any questions, just stick them in the comments below. And then the next section of videos will be on the simplex algorithm or simplex algorithms, as there are a couple. Right. Thanks very much for watching.